So why scheme? Do people actually use this language? Well, they do, or variants. And why are people drawn to these programming languages based on Lisp? Well, because the code looks like just a bunch of symbols and parentheses, you could actually write a program that generates programs. Before we do that, I'm going to teach you one more feature called Quasi Quotation, which is a lot like the quotation you already know. But there's an important difference, which is that you can unquote parts of a quoted expression. So there are two ways to quote an expression. You can use quote, which we saw before, or you could quasi-quote, which is represented using the backtick symbol, which is in the upper left corner of your keyboard. And in many situations, it does the same thing as quote. But here's the difference. Parts of a quasi-quoted expression can be unquoted using the comma symbol, which is the unquote symbol. So this is quote, this is quasi-quote, this is unquote. Let's say I've already defined B to be 4. If I quote AB, I'll get AB. Doesn't matter that I've defined it. If I quote A, followed by the result of unquoting B plus 1, well, this whole thing is quoted. So we're not going to use the value for B. We're just going to write out exactly what's here. A followed by the value of unquoting B plus 1. So here we have a list within a list within a list. But writing the same expression started with a quasi-quote will give me something that I think is more useful, a list A5, where 5 is the value of evaluating the expression B plus 1. Why did this expression get evaluated, whereas A did not? Because of the unquote. So the way to read this quasi-quote a list A followed by unquote plus B1 is that we're going to build a list. That's what we've said here. It's going to start with the symbol A, because that's all quoted. But now, this unquoted expression is going to be replaced by its value. So, by using all the same rules of evaluation that we have already for scheme, we evaluate B plus 1, which can depend on the current environment. B is 4, so B plus 1 is 5. And then we get a list of A and 5, mixing together stuff that was quoted and stuff that was evaluated. Quasi-quotation is particularly convenient for generating scheme expressions. If I want to define a procedure that makes a new procedure, taking in some n, and building a lambda expression that says lambda d plus dn for whatever n is, and then I call make-add procedure on 2, what I get back is a list. A list whose first element is the symbol lambda, second element is a list containing just one element d, and the third who's a list containing the symbol plus the symbol d and the number 2. And quasi-quotation makes it convenient to write new code on the fly. Instead of having it be lambda d plus dn for two different variables d and n, here we have an expression that evaluates to a procedure that takes only one argument, and the n has now been filled in with 2. So here's a procedure that writes code, and it writes code with particular parts filled in. Okay, let's do a longer example. While statements. Well, in Scheme, there are no while statements. But while statements are awfully convenient. Like, let's say you wanted to know what's the sum of the squares of even numbers less than 10, starting with 2. So 2 squared plus 4 squared plus 6 squared plus 8 squared. What would you do in Python? You'd set x equal to 2, total equal to 0, while x is less than 10, increase the total, increase x. And at the end, total gives you the answer to this question, which is 120. How do you do this in Scheme? Well, you want to iterate, but you're not allowed to use a while statement, so you have to use recursion. You have to write a new procedure that takes in x and total. This is the kind of current value of x as you're going through while, and the current value of total. If it's the case that you're still iterating, if x is less than 10, then you make a recursive call, updating x to be x plus 2, updating total to be total plus x squared. If, on the other hand, this is false, that means you're done, well, then you should just return total. But after defining this recursive procedure, I need to call it with the right initial values. Total starts at 0, x starts at 2. And now I've written two expressions instead of one. If I wanted to fit it all into one expression, I would need to use begin. Okay, so it can be done in Python, it can be done in Scheme. I find the Python easier to read. There's nothing inherently recursive about this expression. It just happens to be that the way you express it in Scheme is through recursion. And you could do more of these. What's the sum of the numbers whose squares are less than 50? Starting with 1. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 is still, 7 squared is still less than 50, but not 8. Well, it's basically the same code, except we changed the initial value, we changed the while condition, we changed how we updated total, we changed how we updated x. And so likewise, those things need to change in the Scheme code. But what if there were a bunch of these, and someone told you you have to write Scheme expressions for all of them? Wouldn't it be nice if you could just get Scheme to write this whole thing for you? Well, that's exactly what you could do. So I'm going to start us off with that example that you just saw of summing numbers whose square is less than 50, starting with 1. But I want to be able to define a procedure that creates one of these sum while expressions out of an initial value for x, a condition for the while statement, what to add to total, and how to update x. And how would I call this? Well, I want to call it on an initial value for x, a while condition, like I want to keep going as long as x squared is less than 50. In this case, I'm just adding x to total. And how am I updating x? Well, using the expression x plus 1. I think it should be the case that this call generates this expression. But now we're going to do something interesting. We're going to make this generic. We want to return an expression that starts with begin. And that expression should always say define f as x in total if something, not always this, but whatever condition is passed in. The reason I unquote this is that I don't want the symbol condition in the result. I want whatever's passed in, this expression, in the result. Likewise, I want this expression as what we update x with. So I'll unquote and write update x. I always want to add something to total, but what it is depends on what I want to add to the total, which in this example I think should be x. The fact that I return total when I've reached the end of the while condition stays the same. The fact that I call f starting with total equals 0 stays the same, but I do want this to have some other value. So I unquote and put the initial x here. So now I have a quasi-quoted begin expression, which means that the result of evaluating this quasi-quotation will be a begin expression. But I still need to close the parenthesis for the procedure that I'm defining. Okay, I've rearranged a bit so that I can load this file and make this call. And look what it did. It built for me something. Let's give this thing a name. Result of evaluating this expression. This result is a list. It begins with begin, but it's also code, and when I evaluate that result, I get 28, which is the result of adding 1 and 2 and 3 and 4 and 5 and 6 and 7 together. If instead I wanted that other thing, the sum of the squares for even numbers, up to but not including 10, then I would evaluate something else. the result of starting at 2, having a while condition that says x is less than 10, what I add to total in this case is not x but x squared, and I update x to go to the next even number. This should give me 2 squared plus 4 squared plus 6 squared plus 8 squared is 120. And the way that it did it was to actually produce the code that results in 120, including defining a new recursive function and calling that, and then eval actually defined that function and called it and got the number. So this is an additional kind of expressive power in a programming language, to be able to write procedures that write the code for other procedures. And that's one of those things that get people excited about Lisp and Scheme.